Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Good morning, everybody, ladies and gentlemen. Thank you for your time to join our online seminar. Please apologize that our seminar today is very late to start because there are some problem that we don't know exactly what it was. And the second apology for us is we changed the plan. Previously, we have Dr. Arezoo from Tehran, Iran, who will give a talk today. But because there is some problem, we changed the plan, and there is a college from Bangladesh that will replace or substitute the speaker for today. And of course, I will please Pak Anwar to lead the discussion. Pak Anwar, I think you could start the discussion or the talk and allow the speaker to start. Thank you, Pak Anwar. I hope everyone enjoy the talk and use this event to collaborate to make a network with the others and enjoy again the seminar. Thank you, Pak Anwar. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Pak Bagus, for giving me time for this seminar, and welcome to the seminar of the Department of Statistics IPB University of Indonesia. Thank you of the head for the Department of Statistics IPB University, lecturers, postgraduate students, and participants from Indonesia and overseas. And thank you for Dr. Muhammad Sohail Rana from the East West University of Bangladesh, who will give some talk about the outlier detection in, let me see the topics, outlier detection in high dimensional multivariate data. So I think, sorry for inconvenience caused because of the technical problem from Dr. Arezoo previously, but the good thing is we have also very good presenter today, our speaker today, who will talk about the outlier detection. So please welcome Dr. Muhammad Sohail Rana from East West University of Bangladesh. So time is yours. I think you are still mute, Dr. Sohail, so we cannot hear your voice.
Yeah.
Okay.
Can you hear me now, Doctor?
Okay. Yes, please.
Okay. Assalamu alaikum and good morning. So actually, I was not well prepared since Dr. Anwar. Actually, we worked together at UPM as a lecturer. So suddenly he asked me, to present. So I was not well prepared actually. So I have something actually that previously I have presented. Basically this presentation is for the undergraduate students, and maybe some parts may helpful for the graduate students also as well. So I'm not sure that how much it is useful for the the advanced level learners. Okay. So anyway, can you see my slide?
Yes, Doctor.
Yes. So the topic is identification of outliers in high dimensional multivariate data. So I am working as an associate professor at the Department of Mathematical and Physical Science, East West University, Bangladesh. So this is one of the private university in Bangladesh. So what is outlier? We know that outlier is that something that is different from the normal data points, right? So this is called the outlier. So here is some picture that you can see that is outlier. So that means that all apples are green and then the red one. So it's something different. So that means it's the outlier. Now this is the real example of the outlier. There is a climate data. This data is collected by the Indian Statistical Institute during the years 1990 to 2003. The highest temperature. But what we can see, the highest temperature that is the is 90 degree, 80 degree. so which are impossible actually. So it's very common when we are collecting the data, some data point may be the outlier because of this type of that unusual recording or something like this. So it may be the typing error, or maybe that the recording error. So that's why it happens that often in the real life situation. Okay, so the consequences of outliers actually this is the one that quote from the Hampel event is the the very old the quote that is claimed that the routine data set typically contains about 1 to 10% outlier. So it's actually the very common that data set might contain that 1 to 10% outlier. Okay, so
I think you can give a slideshow of your presentation so it will be more clear.
Yes, I'm presenting the slides. Can you
the slideshow? Just press the slideshow so that it will be bigger.
Oh, okay.
Thank you, Dr. Sahil.
Okay, thank you so much. Okay, so one immediate consequence of that, due to the outliers, that even the data is normal, but at the end we can conclude that that is a non-normal data. So once the data is non-normal, that means the classical inferential procedure might break down, because the most of the classical inferential procedure or most of the classical techniques depends on the normality assumption. We know that. So the due to the outliers since the normality assumption breakdown, that means the classical procedure that might not be reliable, or the inference we draw from the classical approach, it might not reliable. Okay. Applications of outliers. So it can be used in the fraud detection. That just I quote the something that the purchasing behavior of the credit card. If you lost the credit card, maybe someone want to buy the that use the more use of your credit card. It can be used in the medicine, sport statistics, right? Because sometimes when the athletics take the drug, so maybe the his or her behavior might be the unusual. So also it can be used in the sport, the statistics. So also for loan application processing, satellite imaging analysis, and so on. So how to deal with outliers? Detection of outliers and delete from the data. So how we can deal with outliers? So we can detect and then we can delete. This may be the one thing. But the another thing is, to detect the correct outliers, we need the robust method. So that is like I say, actually chicken egg problem, or we call some things like this, that once you have outliers, you need a robust method to detect, or without robust method you cannot detect also the outlier. What is we call the robust method? Those who are familiar, I think it's okay, but those who are not familiar, that what is the robust method? Robust method is something like this, that if I gave the very simple example between the that mean and median, when the data set has that outliers or some unusual points, we usually use the center of the data as a median, not as a mean. So that's why we call the median is a that is the center of the data. Okay, so that is the one thing, the outlier in the high dimensional data. Okay, so the scatter plot of the 3D scatter plot here, sometimes what is the problem? Showing finding the outliers from the multivariate data, because in the multivariate data we have the dimension is probably there is more than 2, say 3, 4, 5, 6, and so on. So it's very difficult to get that the show by the picture that, but there is some ways that we can also reduce the dimension of the data and we can make it or show it in the 2-dimensional approach. So usually we do in the principal component approach is something like this, that once you have the that the more dimension, then we try to show the data that plot the data using the principal component 1 and 2, and so that we can identify the outliers. This is one of the approach that how we show the that outliers in the multivariate data. Okay. But why is it important nowadays? That high dimension is very important, because in the few years ago, I think that we have the storage problem of the data, but nowadays it's a very common. We have a high computational computer, and it's easy to recording the data. So that's why every day we are dealing with the that with the high dimensional data. So that's why it's important. And And challenge in the high dimensional, there is a cause the curse of dimensionality, because in the high dimensional data, the relative contrast between the distance decreases with the increasing the dimensionality, and data are very sparse, too many points are outliers, concept of neighborhood becomes meaningless. So actually in the high dimensional case, when you're talking about the high dimensional data, the classical approach like as that the neighborhood method or maybe the distance method is we cannot just use a straightforward because of the high dimensionality. So the solution is use the more robust distance functions and find the full dimensional outliers, or maybe the find outliers in the projection or subspace of the original feature space. So actually I'm highlighting this point because in the some approach that is called the projection of space, once we have the full dimensional approach, then we go to the subspace that is called the subspace, and from the subspace, so subspace is like this, there is not the full dimension. Suppose we have the data is n by say n by 50, then maybe we go for n by 20 or 10. So that is a subspace, and based on the subspace we try to find the outliers in the subspace. So outliers in the high dimensional data, these are the methods actually: the distribution based approach, depth based approach, angle based approach, then distance based approach, and lower dimensional projection approach. So especially I'm talking about here the distance based and the lower dimensional projection approach, but I'm not going to discuss in the others. So there are some advantages and disadvantages of the all methods, but I want to escape the some slides. I'm not going to discuss those. Okay. Distance is very common when we are talking about the distance. At first, it comes to our mind about the Euclidean distance. Okay. So we know about the Euclidean distance, that how we can find the the distance between 2 points. Suppose here we have a point x1, y1, and another point is x2, y2. So how we can find the distance? So it's very common. So now the problem of the Euclidean distance. Look here is the one thing that point 1 and point 2 have the same Euclidean distance from the centroid, right? So now if I ask the question that which point is near from the data center, okay, which points are near from the data center is the, so using the Euclidean distance, if you see the Euclidean distance, so here is the Euclidean distance, the circle one, it means that both data points are close to the center, but if we use the statistical distance, that is not the case, because point 1 and point 2 do not have the same distance from the centroid in terms of the data variation. Now when we are talking about the statistical distance, at first we have to think about the variation of the data. So now if you look the variation of the data, so that means that from the center, from the point 1 and point 2, we don't have the same variation. So that's why we rely on the statistical distance instead of the Euclidean distance. So Euclidean distance means that we do not consider any variation of the data. Now, once we are talking about the statistical distance, we that talk about the variation of the data. So I'm not going to discuss maybe this point so much, and also rotation. I'm just escaping this slide. Then one important distance is Mahalanobis distance, which is very common to detect the outliers, either in the low dimensional or high dimensional data. So here is the one that example, the surprising amount of radiation emitted when the doors of the microwave ovens are closed and open. We are using the everyday microwave, right? But if you open the door and close, that there are some radiation may spread from the the microwave, which is harmful for the body. So here is the data that when during the door close and door open, and then I apply the Mahalanobis distance to detect that which microwave is that giving the unusual behavior or something like this. So we can see that the red marks. That means using the Mahalanobis distance. that these data points are we can consider as outlier. So that means the radiation is not that in normal. So that is the giving the that high radiation. Here is a counter plot. The same thing actually I'm presenting. Now, what is the problem with classical Mahalanobis distance? Because we all know about the Mahalanobis distance, so this is not nothing that new. But the thing of the thing is in the when you are using the Mahalanobis distance, classical Mahalanobis distance, the thing is that we have some problem of masking and swamping. Masking effect means that an outlier is undetected. Okay, so in the data points there is an outlier or there are some outliers, but it's undetected. That is called the masking problem. And what is the swamping problem? It means that the good observation is incorrectly identified as a outlier. So that is the swamping problem. So the classical Mahalanobis distance actually is suffer from this problem, that is a masking and swamping. And it has been that also that discussed in the different literature that classical Mahalanobis distance is not good for detecting outliers once we have a masking and swamping problem. So as a solution of that, because we know that about the Mahalanobis distance, I think somewhere is written the formula, I'm not sure. Okay, in the classical Mahalanobis distance is depends on the variance coverage matrix and the mean vector. But instead of mean vector and that variance coverage matrix, now some authors like as the Arezoo, they propose the MCD estimator. So that is called a minimum covariance determination. So they try to find the best set of the variance covariance matrix from the best set of the data. So that means there is some combination of the data and they try to find out the best set, that which set the set is free from the outlier. And based on this set, they try to find the that variance coverage matrix and the mean vector, and then they showed that using the MCD estimator, the Mahalanobis distance is more effective than the classical form. Okay, and also, but what is the problem of the? Also, there are some others. That a classical approach we call that that fast MCD, or maybe we have also MV estimator. But the problem of these methods also for the high dimensional case, because most of the method like as MCD or MV or other subset types of method, because these types of methods are subset based method. At first they try to find the best subsets of the data, and from the best subsets of the data they find the variance coverage matrix, and then they use these variance coverage matrix and mean vector inside the that Mahalanobis distance. But the problem of that this type of MCD or MV estimator, because they use the subset, that is this combination. So once you have a high dimensional data, so computationally is that sometimes it may be impossible, because if the data dimension is very high, that that sometimes it takes a the very long time, even if you put the one set of data, because if it has the very big combination, NCS combination from the that high dimensional data, sometimes it is actually practically is not useful. So that's why this is the problem. So what is the solution of that? As a solution of that, we can use the some lower dimensional projection method. So this type of algorithm, that you can also see that that is the some methods like proposed by some others. Okay, now okay. Okay, there are also some methods, and also they have some limitations. Say when you are using the Mal route, right? Okay, this types of the method is very common in the R package also. So they try to actually basically they try to reduce the computational burden. And in 2000, I think I forget the idea. What is the? I think Fieldsmore, he proposed a very effective also method in 2008, and it shows that this method is better than the other method that is proposed by Pena 2001, and also the other methods. Okay, he showed in his paper. Now I try to find also the outliers and slightly I modified the fields more approach, that in the lower dimensional approach. So those who are not, that familiar about the lower dimensional projection method, a lower dimensional projection method is what I have said, that once you have a full dimension, then we go for the lower dimensional, and one of the approach is called the PCF. So basically, I'm talking about the singular value decomposition here, because once you have a matrix A means that here we have a full data matrix, and then we go for the singular value decomposition, and we know that the singular value decomposition has a that the power of reducing the data dimension, not losing that much information for the informative purpose. What does it mean? We know that for the I'm not going to discuss about the spectral decomposition. So I just skip these slides because of the time limit. So in the singular value decomposition, basically what we do, here I give you some small example. This is from the book actually, and especially for the undergraduate students. Actually, we try to split the data into 3 matrices. So if there is a matrix A, then we try to split something like this, right? And we know that in the singular value, we call the matrix you can see in the middle. Actually, sorry. This is the singular value that we can decompose into matrix, that U lambda V transpose. U is a orthonormal matrix and lambda is a diagonal matrix. And singular values, actually we call this is the eigenvalues. These eigenvalues we call these the singular values. And eigenvalues is very important. That when you are reducing the data, if you know about the principal component approach, we know that based on the eigenvalues, we try to that find out that which principal component is, how many principal components are appropriate. So we are doing the same thing actually here. So now the one application of that, if I just quickly show, that is the application of SVD. So here is my picture. Say that is the picture. Then I try to the read using the singular value decomposition. Now you look at it, this is the rank 50. So that means I use here the the mode dimension, but still when I am using the rank 15, but here I am using the low dimension, but still I can see this is my picture. So one of the important thing of the lower dimensional projection method, why is important, because at the end we try to find some conclusion, or maybe try to find our output. But the thing is, when you are detecting the picture, even I'm reading in the lower dimensional approach, I can see this is my picture. So that is my objective. I want to identify this picture. So that means this is important. Even I'm reading this picture in the rank 15, in the lower dimensional, so still I can see this is my picture. So this is the important application point of view, because we are reading the data in the lower dimensional, but still we are getting the same that confirmation that this is my picture. So that is the motivation behind the detection of outlier using the lower dimensional approach for the high dimensional data. Now I'm talking about the Fieldsmore approach. So we can see in the R package also that PC out, but I try to modify this approach slightly. Okay. In the proposed method, we'll find a low rank matrix, which is good approximation to the data matrix A. So I haven't, that discussed my method. This is the ongoing, my research. So actually, at first, I propose that a low rank matrix, which is good approximation to the data matrix A. Good approximation means that actually we have to think when you are transforming the data high dimensional to low dimensional, then you have to think that how much variation you are losing. So this is the one of the important thing. For this purpose, we find the orthogonal matrix of the X transpose X, which is the first orthogonal matrix of U of the SVD. So this is the SVD from, after that we are trying to find actually the SVD matrix, and this is the first that orthogonal matrix. determine and retain only those p singular values that contributes at least 80% of the variance. In this case, what we are trying to do, we want to retain the p singular values, those contributes at least 80% variance. But in the Fieldsmore approach, actually in their approach, they try to contribute actually a 90% variance. So once I compare with my proposed approach, with the slight modification from the Fieldsmore, I found this is more effective than that one. Still haven't published, and I mean that I'm not doing the final simulation. So in the proposed approach, basically the good thing is that when we are talking about the multivariate data, and if we first transform the data, that into the using the that how we can transform the data by subtracting the mean and then divide by standard deviation. So there's actually we try to standardize first. Now, once we are standardize the data, simply we can expose this as a Mahalanobis distance, because here the variance covariance matrix in that the diagonal elements will be 1, because we know that once we transform the data, then it follows the also the normal distribution with mean 0 and variance 1. So since it is a mean 0 and variance 1, so that means that we can just show this is the Mahalanobis distance. So actually the method is based on this, that we transform the also the transform the data first, and then try to use the SVD approach, and then find the Mahalanobis distance. But one thing is that once we are transforming the data and using the Mahalanobis distance, we know that Mahalanobis distance follows the chi-square distribution with p degrees of freedom. But once we are transforming the data, so it's not necessary that it follows the chi-square distribution. So actually the different types of cutoff points also the proposed. Okay, so we found that in our approach that this cutoff points also the proposed by Merona. Actually I tried to find also another cutoff point, and this is maybe the suitable for my approach. And then here I generate some data from the P10 to P1000. That means that is our number of variables, that minimum is 10 and maximum is 1000. And based on this data, I just put the 100 simulation. Okay, and of course the data is generated from the multivariate normal. And here is the sum result, that SVD out and PC out is proposed by Fieldsmore. And when I am comparing with this method, that is the different standard deviation, and you can see the result when I am giving the that 10% outlier. So when I'm giving the 10% outlier, and my method correctly detect here the 10%, 10%, 10%, and for this case actually slightly that more, but it's still better than the PC out. And also here the 10%, but PC out is, we can consider this method is that detecting more outlier than the 10%. So this is actually the comparison that you can see with my method. So here is another example that P is 50, right? So it shows that when I'm using increasing the dimension of my data, and here is N is 1000, and even my method is performed better than the PC out method, which is proposed by the Fieldsmore in 2010. And also here I use the P50 and 1000. Still I can see that my method is better than this. Okay, then yeah, here is the some that comparison, that all the simulation I use, that I can see that my method has the great ability to detect the outliers, and we have the 10%, but the PC out method is slightly more. Okay, so I think that's all from my presentation. So if you have any questions, maybe you may ask.
Yeah,
Dr. Anwar.
Yeah, thank you very much, Dr. Sohail. Very interesting topic actually in the outlier detection for high dimensional data. So I think we can arrange like this, Dr. Sohail, because now Dr. Arezoo is already with us today. So we will have her talk now, and then maybe the Q&A session will be allocated after Dr. Arezoo's talk.
Okay. So
thank you. Anyway, very interesting topic. So we will accumulate all the questions maybe after the Dr. Arezoo's session. Thank you very much, Dr. Sohail.
Thank you, and
topic.
Thank you all. Okay, thank you.
Okay.
So okay, sorry that I have to leave also.
Okay. Can you still with us until I don't know whether you
I
can
think
still
another 20 minutes maybe I can be with you, because I have also the class, because since I present suddenly.
Okay.
So okay, I'll try to that stay sometimes maybe. Okay, thank you.
Okay. Anyway, when there is a question, maybe the participant can give me the text in the chat box.
Yeah.
So
sure.
if not current time, maybe your question can be answered, maybe can be responded, maybe after the session. I can pass it to Dr. Sohail. Is it okay, Dr. Sohail?
Thank you, Doctor. Yes, sure.
Okay.
No problem.
Okay. Thank you. Anyway, Dr. Sohail.
Thank you.
So now Dr. Arezoo is already with us. So Dr. Arezoo, can you hear me?
Yes, I don't know. This is clear, Dr. Anwar?
Yeah. It is clear, very clear, Dr. Arezoo. So you will have your talk very soon. So let me just read your very brief CV. So Dr. Arezoo was graduated from PhD in statistics, in applied statistics from Mathematical Institute of University Putra Malaysia. Previously, she was expert of Statistical Center of Iran with more than 10 years of experience, and she has been working in National Population Institute of Iran since 2013. And now she is Associate Professor and Director of Statistical Method and Population Modeling, Department of National Population Institute of Iran. And of course, she has more than 50 articles about the modeling, demographical data, and then 2 books in respondent-driven sampling methods. And her fields of interest are hidden population sampling, machine learning, structural acquisition modeling, and also robust statistics. So currently, the flyer, she is a director of Population Institute in Iran, in Tehran. So now, please welcome Dr. Arezoo to give your talk. Time is yours.
Is my voice clear now, Dr. Anwar?
Yes, very clear. Please.
Okay. Assalamu alaikum and very good morning to all the audiences. Please accept my apology for late connecting. I don't know what was the problem, but thanks also Dr. Sohail for covering my late. And let me share first of all, because I know that we are short in our time. So it's better to just share my screen and we see also my presentation slides. Okay, let me share it. I don't know, you could see the screen or not?
Yes. Yeah, I can see it. So please do it with the slideshow. Okay, I think it's very clear.
Okay, again, I thanks Dr. Sohail and accept my apology for any inconvenience that happened today. But today I'm going to talk about random survival forest in analyzing first birth interval. And before going to my presentation, I took this opportunity to thank Dr. Anwar for arranging this online seminar of machine learning for survival analysis. Actually, I'm going today to talk about the result of a survey which has been done in our department, the Department of Statistical Method and Population Modeling in National Population Research Institute of Iran, which has been done this survey in 2020 with the collaborating of Dr. Mahsa. Today I'm going to cover these contents. I will briefly talk about machine learning methods. I will focus on just supervised machine learning methods. Then I will go and talk about conjunction between these machine learning methods and survival analysis methods. Then I will talk about survival trees and find some disadvantage of survival trees. And then I will talk about different survival forest algorithms, but I just focus on three most applicable ones. And then I will implement these algorithms to my secondary data, which has been gathered and collected in our institute, which is about Vim's first birth interval. And then I will conclude that which predictors was most important in the prediction of this first birth interval of women. But what is machine learning? Actually, what is the topic about? It is a branch of artificial intelligence which was born in 1980. And it's a way to get, for sure, artificial intelligence. And its algorithms learn from interdata and then use the knowledge and actually information to draw conclusion for new data set. And the machine will learn by imitating the way humans learn. Three different branches of machine learning exist: supervised and unsupervised machine learning branches or divisions are the most applicable machine learning methods that I will focus on supervised machine learning today. About supervised, we know that a teacher or supervisor should exist in the algorithm, and we know that the interdata or training data and also the outcome is known for the algorithm, and just by predicting the outcome again by the trained data set, we could conclude about the a new data set. But in unsupervised machine learning, we know that here there isn't any supervision or teacher, and the label of the interdata set is not clear or unlabeled. And according to clustering and the dimension reduction, these two methods we could label for our data. But in supervised actually methods, we can use two different methods of classification and regression methods. I want to, by an example, talk about this supervised learning machine learning method. Consider that we have a basket of fruit, that different kinds of fruit exist in this basket, but we are limited to apple, pear, and also mango. And we are going to train our process with this basket, which is our training data set, and train our process and find a method according to the shape and also the color of this fruit to divide it to different kinds of fruit. For example, according to the shape of a mango or color of mango, we for a new data set or for a new fruit, we can conclude or predict that it's this fruit is a mango. If a new fruit has given to you according to a white shape and maybe a pale yellow color of the fruit, you can guess that, or algorithm can guess that is, or predict that is mango. These different steps exist for supervised learning. In step 1, we should be sure that what is the category of the training data set. We should collect a well-labeled training data set. In second step, we know that from the first full data set will be divided to training data set and testing data set. In train data set, in step 2, it will be divided to training data set and also validation data set. In step 3, we should determine that which characteristics from the training data set we should use to help us modeling and predicting correctly. In step 4, we should discover that which algorithm is suitable for our study. Maybe we could use classification like a decision tree algorithm or regression algorithm. In step 5, we should implement this algorithm to our training data set, and using this validation set that we have divided our training data set in step 2 to 2 parts. One part is validation set, to use it as a control to control the estimation parameters and preventing overfitting. And in the last step, we should evaluate our model accuracy that we have found it in step 4 and implemented in step 5 to our new data set, the test data set, and we should seek that is correctly could find the output, and if could predict correctly the output, then we can tell that our algorithm is accurately could predict. In supervised learning algorithms, 2 different groups, as I told, 2 different branches exist. In classification, the aim is assigning each of the data to a category. A trained model or classifier could be used to classify data pointing to different groups. And in regression algorithms, our aim is prediction of an outcome, which is the numerical variable. In classification, as we could see, decision trees exist in classification because the output is classified, and in regression trees or random forest could be considered under the regression supervised learning algorithm. I want to make a conjunction between survival analysis methods and also this machine learning. But before going to make this conjunction, it's better to talk about what is time to event data and what is survival analysis. As we know, time to event data are those positive, continuous, actually variables that event time interval censoring and time varying predictors are matter for these kinds of data. And we should use survival analysis, which are the statistical approach which used to investigate the time to takes for an event of interest to occur for such a kinds of data. In our case, because we are going to talk about first birth interval, our event is first birth interval, the time from the marriage of a person or women, here we consider just women, up to the time that give birth to her first child. This is the time interval. And censoring also in our case, right censoring will happen, and we should also be aware that maybe our predictor could change with time, and time varying predictors also could be modeled in such a disguise of method. But what is right censoring? If we consider beginning of our study as this 0 months after the marriage time, exactly at the time of the marriage of the woman, till the time of our end of our study is 44, for example, 45 months after the marriage is our end of our study. If any of women can see and can give birth to her new baby, her first baby during this time, so observe the event. But if after end of the study, see, or maybe in some of the cases they are childless, forever. So maybe if in these kinds of cases we will face right censoring, and in time to event data, as we know, our outcome has two different elements of time and censoring, and also the censoring status, which could be defined by delta I. If it is equal to 1, it means that that a case has observed the event. When it is equal to 0, it shows that censoring will happen. In our case, we will face right censoring. But about survival analysis method, statistical, I'm sure that all the audiences are familiar with statistical methods under survival analysis methods, such as non-parametric, semi-parametric, and parametric methods. And about machine learning, which is a branch, non-parametric branch of survival analysis method, we just going to focus on survival trees here. And before going to survival analysis and maybe survival trees, we know that survival function is the probability that the instant can survive for longer than a certain time t, and hazard function is the probability that event of interest occurs in the next instant given survival to time t. We need cumulative hazard function in our algorithm, so it can be defined as the integral of this hazard function, and we will use it in our algorithm. But we should know, because we are going to use this survival forest as an alternative of a semi-parametric approach, that the most applicable method is Cox under this semi-parametric approach. We should briefly speak about survival analysis statistical methods, which are non-parametric, semi-parametric, and parametric approach. We know that in a non-parametric and semi-parametric approach, baseline hazard, no need any assumption, but in parametric approach, as we know, different distribution could be defined for this baseline hazard, could be variable, gamma, or normal distribution. And about the covariates, non-parametric method doesn't need any assumption on covariates, but here in Cox, we have to know pH assumption, and we have to check pH assumption, proportional hazard assumption, which is if we have two different cases, if the ratio of the hazard of these 2% should be independent from the time t. But tree algorithms, if we see, and better to talk about how tree algorithm works as a whole story. Okay, here make it clear that how it works. If we have the data set, we should prepare our data set, and the most important part here is handling missing data. After actually here we should split the data set into training and testing data set in first step, and use actually a specified model before, according to which tree we are going to use. For sure we predict different outcomes, and after we grow in fully our tree, we will find that in each of the nodes of the tree which predictors we can see and present, and they are for sure the most important predictors in our outcome. But as a very simple example, I'm going to talk about survival of passengers on the Titanic ship. As we can see here, there are three predictors of gender, age, and also the number of siblings aboard with these actually passengers. They are these three actually predictors present in the these three, and they are the most important predictors for sure in this study. In the root, we can see that gender has seated as the most important, and in the as a root actually predictors, and it has two as a parent nodes. It has two daughter nodes of age, and here is terminal node. if the case or the passenger was a female, 73% probability exists for that passenger to be survived. But if he was male and he was more than almost 10 years, there isn't that much probability to be alive. But if it is less than or equal to almost 10, and the number of his sibling was less than 3, 90% probability was for that male person to be alive. However, if the number of siblings was more than or equal to 3, for sure he was died in this ship. So different trees could be defined according to the output of a study. If the output is classified, classification trees or decision trees could be defined. If the output is continuous regression trees, and if we are working with time, for sure, especially here with right sensor, actually time, we should use survivor trees. But there are CART algorithm, very familiar and very one of the most applicable decision trees in the literature is CART classification and regression tree that we can use it for classification, classified outcomes and also continuous outcomes. In 1985, survival trees has been defined according to this CART by extension of this CART, and it is a non-parametric method. It's not that much complex. It could be interpreted easily, and actually it doesn't need any structural assumption, and also it could work with different kinds of predictors, and interactions doesn't need to be defined at first in these kinds of trees. And this is the whole story that is true for all different kinds of also trees. But if we want to introduce a single tree actually has some bias in the estimation and has some problem for the variance of estimation, and is not that much powerful as a prediction. If we consider prediction, is not that much powerful. But if we go to actually make it this single tree to make it 1,000 tree as a forest, then the power of our prediction will be higher, and we will improve our learning performance in this case. A random survival forest by Bremen in 2003 has been actually introduced by extending a CART model and also random forests as the powerful predictions and methods, and randomization has been added to this algorithm due to this fact that we wanted to make bootstrap actually samples uncorrelated and make the correlation bias less. 3 different survival forest algorithms exist in the literature: RSF1, RSF2, and CIF. In RSF1, we could use log-rank statistics as partition rule. In RSF2, we can use log-rank square as partition rule. And in CIF, unlike the other 2 RSF1 and RSF2 method, in CIF conditional inference survival forest, we can use a test statistics to find and divide parents node to the daughter's node, and when actually RSF1 and RSF2 make some bias when we have predictors which have more classification or levels in our study, and CIF can cover and also solve this problem. But how the algorithm of a survival forest algorithm works, as we mentioned it before, if we have a sample, actually we can generate n3 different actually bootstrap samples from this sample or original sample. And in each of the samples, we could put almost 60% of the sample as training data set, and we could grow the trees according to this bootstrap sample result, and 40, almost 40% of our sample as out-of-bag samples. And we can use these parts of our sample for finding prediction error curves, or also we can find prediction performance indices that I will introduce them. But how it will grow the tree, we know that randomly in this for each of the trees, randomly a square root of the number of predictors will be selected as parent nodes in each of the first levels, and then by splitting rules such as Lagrange statistics or Lagrange square statistics, we could find parent, actually a daughter's nodes, and we can fully grow in the trees in different ranks and levels up to the time that in terminal nodes we don't have actually more than actually a pre-specified number of events. Up to that time it will be stopped, and cumulative hazard function will be calculated for that tree, and for all entries ensemble cumulative hazard function will be defined. From out-of-bag samples we can find prediction error and also prediction performance indices such as C-index and also integrated barrier score. For C-index, we will define two different actually indices. C-index has been defined for algorithm in 1982 to measure and evaluate the prediction made by an algorithm. Actually, it's 1 minus error rate. When error rate or this C-index is half 0.5, it shows that this algorithm doesn't work better than random guessing. And when error rate is 0, it shows that perfect or when C-index is in this way is 1, it shows that a perfect prediction exists. If we want to talk about how it works, if we consider all the pairs in I and J pairs in our data set, we have time to event and also risk squares time to events of this I and J could be defined as Ti and Tj, and risk score is eta I and eta J. If both of them are not censored, we know that when risk of I's case is more than J case, so the time of event for that person should be less than the time for J case. So these kinds of pairs are concordant pairs, and if Ti is more than Tj, they are discordant pair. If both of Ti and Tj are censored, they are not actually acceptable, and we will delete these kinds of pairs from our study. And if one of them are censored, we should say that Tj should be more than Ti in this case to be permissible pairs, and if in this case if eta I is more than eta J is concordant pair, and if eta I is less than eta J is this concordant pair, and C-index could be defined as the number of this concordant pair over the permissible pairs. When C-index is near almost actually very close to 1, it shows that the prediction was better. Integrated barrier score also could be defined as the average score distance between the observed survival status and predicted survival, which has some weights which comes from Kaplan-Meier weights, and it's the value which is between 0 and 1, and this like to see index when it is near to 0, it shows that the prediction is better, and integrated could be done over the whole trees according to this equation. But we have to actually introduce two other measures as a variable importance and minimal depth to find the most important predictors in our study. Variable importance is actually gives us the contribution or importance of any of the predictors in our outcome. How it could be find actually according to the some noise that we make for our predictors. We could calculate the amount of change that will happen for our prediction error, and it could be divided to actually the measure is positive, negative, or also zero. If it is zero and negative, the amount, it shows that that predictor is not that much important in our study. But if it is positive, it shows that that predictor could be important in our study. In minimal depths, also this measure is the distance from a root node to a node where it is used for the first time for each predictor. Could be defined for all different trees in our algorithm and for the forest, and then averaged and minimal depths could be after that could be reported as an average value. In this example, we could see that coal predictor has been seen in the second level for the first time. However, Billy has been seen in the third level, so for the first time. So we could conclude that coal is much more maybe important comparing to Billy in this study. But what was our data about? We are going to implement these forest algorithms that we introduced to a secondary data, which has been collected in 2017 in our institute under the title of A Study of the Socio-Economic Effects on Fertility Behavior in Tehran, Iran. 1,200 men and women by two-phase stratified sampling method, PPS, has been collected their information from 10 regions out of 22 regions in Tehran, and according to the development level of different regions in Tehran. And the constructed questionnaire has been was used in this actually survey, and the validity and reliability of the questionnaire was proved. But in our study, because we are going to talk about first birth interval, the time from the marriage until to the time of giving the first child birth of any of the women. So just women, 610 women has been analyzed in this study according to 15 predictors that existed in the questionnaire, and we had this trend for first birth interval in different researchers in actually literature review that this first birth interval from 2000 up to 2015 is was increasing. In our study, almost 23% of women were childless, so right censoring was 23%, and according to survival plot of first birth interval, women first birth interval, we've seen that this first birth interval for 88% almost most of the women in our study was less than 5 years, and this Kaplan-Meier median of this first birth interval was 38 months after marriage, which comparing to 2015 was increased also. About descriptive statistics, most of the women were in their 30 to 39 years. They married in 20 to 29 years. They had a diploma. Their partner also had diploma and above. Actually, they were unemployed. They were living in developing and middle developing area. They were renter. They were living with non-family partner. They were forced. Their race was forced, and they thought that they married on time and their family expenditure was less than 2 million 2 months in 2017, according to our currency. And in univariate analysis, we've seen that the age of woman, educational level of woman and her partner, and also the activity and also region of the region was significant predictors in this study. And then we can actually, this is also the same result which has been shown in the graph. First of all, in multivariate actually level, we implemented Cox proportional hazard model in our data set, and we've seen that according to these 15 predictors, just age and also kinship was significant in our study, and these two predictors, before going to any interpretation about the result, we should say that pH assumption is truthful. All the predictors in our study, as we've seen for age at first marriage, kinship, and also partner race, and also marriage time attitude, was not pH assumption fulfilled, and these predictors actually were dependent to the time. So CPH result was not valid in our study. So as an alternative, we could go for random survival forest algorithm that could be actually use random forest and party package could be found in these two packages in R. We have used these package in our study to implement these three different random actually forests in our study, and we've seen that according to integrated barrier score, the least amount of integrated barrier score is for random survival forest one, that one that use log rank statistics as splitting rule, and about the same day also the largest amount is for RSF1, so we consider that RSF1 fit for our cases, and we can convenient for our case, so we have used RSF1 algorithm in analyzing first birth interval. As we could see after implementing RSF1, according to variable importance, the most important variable are age and educational level here in our study, and the least important variable are sex preference, race, and ideal birth interval in these 15 predictors, among these 15 predictors. And according to minimal depths in this plot, we can see that ideal birth interval and migration status both are not that much important in our study, and ideal birth interval according to both measure is not that much important. We considered not to put these four predictors for our further studies, and one of the most important results here is age of women according to both measure is the most important variable on first birth interval, and the rank of house ownership and partner educational level in according to these two measures is similar. So maybe I've spoken already about the conclusion, but for the last word, I want to add this points that we were going to find an alternative method instead of using Cox proportional hazard method as a semi-parametric survival analysis method in our study, and we have defined non-parametric method actually, which is a machine learning method also as a survival forest, and different algorithms, three different algorithms have been defined in in our study, and according to the prediction performance C-index and integrated barrier score indices, we have found that random survival forest, which use log rank statistics for splitting rule, is fitted and suitable for our study. And from that, we have found that the age of women was the most important predictors in according to VIMP and minimal deaths measure in this study. There are two different published articles. One of them is Juni biomedical journal in which has been an article which has been published in Juni biomedical journal, and the other one is has been published in International Journal Fertility and Sterility. These two articles are available, and if any of audiences wants to use them, then they can download it from their website. And the last but not the least, thank you very much from all the audiences, and please accept my apology again for a late connecting to the server. Dr. Anwar, I'm here if there is any question.
Yeah, thank you very much, Dr. Arezoo. Very interesting topics and very clear explanation about your research interest here. So I think now we can open a Q&A session for both speaker today, for Dr. Sohail Rana with the topics of outlier detection in high dimensional data. And then the second speaker was just now, Dr. Arezoo, with machine learning for survival analysis. So please, participants, if you have any questions, you can either text your question in the chat box of the Google Meet, or you can directly voice out your question, please. Yeah, you have any questions, participants? So please raise your question here. So maybe a question first from me. When you talk about the response variable, you explain that can be categorical, can be continuous. If, especially for the survival analysis, the response variable is time to event, right? Okay, so the event here is the marriage and the first birth, or only the first birth, so that you can calculate the interval.
Actually, here the event was first giving first birth to the birth to for any of the women. So the time between their marriage for each of the women, from the marriage time till the time of giving the birth to their first child. Okay, this time interval was their first birth interval. Consider, for example, after 38, because the Kaplan-Meier estimates in our study for this first birth interval was 38 months. Consider that from the it was the median 50% of our women had at least 38 months from their marriage time to they give their first child. So after 38 months after their marriage, just their first child was born for them. So this was the time interval and our outcome here in our study.
Okay.
I don't know. Clear?
Yeah. Then is it applicable when say the first? I mean. The interval you calculate is between the first and the second birth. Is it possible to do that?
Yes, actually, could be done. Also, we in our actually department we have different actually surveys we have done in about this topic. Also, we have some surveys that just we focused on the second, because mostly women they like to have at least one child, and second child is much more important for maybe population scientists to talk about, or maybe third one in our study and also in our country. We can also define the same thing from the same interval from the time of the giving birth to the first child till the time of the second child, but maybe considering just this interval without considering the first birth interval, and without correlating it with first birth interval is not that much correctly and makes some bias in the study, and it's better to use recurrent methods, recurrent survival analysis methods for second and third and so on first birth intervals instead of just Cox model.
Okay, thank you. It is very clear, Dr. Arezoo. There was, there is a question from the participant now, as you can see in the chat box. There are several things I want to know. First, from your explanation, and I had time to read your journal, your article, you compare KM, Cox proportional hazard, CIF, and RSF. Is the data set divided into training data and test data for each method used, or only on the CIF and RSF? So please explain about that, Dr. Arezoo.
Actually, if I think this question comes from the prediction curves that is I also explained it in my explanation, and also I had it in the slide because I compared these four methods. Yes, in the we can have also for Cox proportional hazard also we can divide the data set into training data set and also testing data set, because we want to find this error, but the algorithm here because when we will put it in the same package, our package, when we want to find the prediction error for example for a random survival forest or a conditional inference forest, I'm not that much sure that they do the same, but because the package is similar and from the same package it comes, I could guess that yes, they will do the same thing. Okay, and
yeah.
Shall I ask the second question?
Yeah, there is a second question. Which one is better between VIMP and the minimal depth?
Actually, we can tell that which one is better and is the best one if we could consider more indices, and according to the more indices, then we can conclude that which one, which variable is the most important. Maybe it's the best, because the last plot that I explained, maybe this plot is much more applicable, and I recommended to use it if you are going to compare different methods together. Is better to use this plot actually, which consider both measures, actually variable importance and minimal depths together in one plot, and according to both plot then decide that which variable, as we could see, age of women according to both measure was the most important predictors in our study. So we could be much more sure that for our further studies, for sure we should be aware of about the women's age in first birth interval, and we should consider these predictors in our further study. I think it's better to consider more and both of these measures together. In the last, I recommended to use the last plot for getting any actually conclusion.
That is very clear, Dr. Arezoo. Thank you very much for the explanation. So there is also a question for Dr. Sohail. Dr. Sohail, are you still in the room?
Yes, I'm still in the room.
Yeah, I think there is a question. I think let me read the question again from Mr. Reza Felix. Two questions from him. First, how many outliers should we consider, and can a significant effect to our model? I think we only have one or two outliers if they won't have a significant effect. And the second question is, especially when we have a large data set, how to choose the most appropriate distance method for our data? Why we don't use Sebisef or mean
Mean-correct distance.
Yeah, distance.
Actually, I have answered the question in the chat box, right? The first of all, that in the high-dimensional data, if we have the only one or two outliers, of course, one or two outliers maybe does not have any effect. But when you are talking about the high-dimensional data, so it means that it's more common to, that the more chance to get the outliers in the data set. So you are collecting so many information, and there is a big chance that you will get the some, that recording error, or maybe that due to the other thing. There is a, the big chance that you will always encounter with the large percentage of outliers. So large percentage means that 1 to 10% may be the more common. And even it is a 1% outlier, so in terms of the high dimensional data is a huge, that if the data dimension is how. So there's the first one. And second question is that about the using the different types of distances. I'm not so sure about that, but using the Mahalanobis distance in a different respect is a more common. Thank you.
Yeah, thank you very much, Dr. Sohail. So please, participants, if you have any question, you can either text it to the chat box, or you can voice out to our Google Meet, please. So for your information, Dr. Sohail and Dr. Arezoo, here the organizer of this event is Department of Statistics, IPB University of Indonesia. We have undergraduate in Statistics and Data Science. We have master degree in Statistics and Data Science, and we have also a PhD program here. So we have quite a lot of what we call students in undergraduate as well as master and PhD students. Okay, so please, participants, if you have any question. So I think there is no more questions, Dr. Sohail and Dr. Arezoo. So if you do not mind, can you please share your presentation material as well as maybe your paper here? Maybe I think there are many people here interested in your research. So perhaps if you do not mind, you can share your presentation slide as well as your paper, if you don't mind. Is it okay, Dr. Sohail or Dr. Arezoo?
Yes, Dr. I can share my one.
Okay, thank you very much. Yeah. So anyway, thank you very much for your time and also your contribution in our seminar. So perhaps that is all from me as the moderator. And the next is I give the time to the organizer to arrange the next step. Please, maybe Dr. Bagus Sarton.
Yes, thank you, Dr. Anwar. And of course, thank you very much to Dr. Arezoo and Dr. Sohail for very nice talk. I learned a lot from both of you. I think all of the audiences also learned a lot about what is the outlier detection and what is the random forest for survival analysis. I learned a lot of new things from both of you, and please allow us to give you a very simple token of appreciation from us, from the Department of Statistics, IPB University. This one is for you, Dr. Sohail. Thank you very much for
Thank you so much.
Your presentation, and also please for Dr. Arezoo. And this is for you, Dr. Arezoo.
Thank you so much. Thank you so much. Nice.
we will send the digital file to your email, Dr. Arezoo and Dr. Sohel. And
Thank you
of
so
course,
much.
also thank you for Dr. Anwar Fitrianto, who lead the discussion of the seminar today. Thank you very much.
Yeah.
And for all of you, all the participants who want to have the certificate for this seminar, please follow the following instruction. So you can claim your certificate by visiting this website, ipb.link/seminar STK IPB, and you will have a form to be completed, and don't forget to input the keyword to claim the certificate. This is the keyword, machine surf. Please ensure that all of the alphabet is in capital letter. You can claim the certificate until tomorrow at 18 o'clock, 6 in the evening. So, and hopefully you enjoy a lot this seminar. And again, thank you a lot, Dr. Arezoo, Dr. Sohel, and also Dr. Anwar Fitrianto. And by this presentation, I think we will end the seminar. And again, thank you very much, Dr. Arezoo and Dr. Anwar Fitrianto. And also, of course, for all of the participants in the Google Meet or in the YouTube. Thank you very much again. And officially, I close the seminar. Assalamualaikum warahmatullahi wabarakatuh.